of 38 working on Woodward's general purpose turbine trip actuator project. My name is Krista Rorty.
I'm Ainsley Birch.
I'm Jason Bono.
I'm Emery DeCare.
I'm Jacob Brooks.
I'm Weston Dole.
Overspeed protection is an essential aspect of a steam turbine safety system. Failure to protect against overspeed causes catastrophic damages that are deadly and expensive, as you can see in this example image. So clearly you want to protect against overspeed to save money, but most importantly to save lives. Trip actuators are the safety devices that control the steam supply valve to the steam turbine. So these actuators are tripped and close the steam supply valve, shutting off steam supply to the turbine when overspeed occurs. Currently, most of these trip actuators are hydraulic solutions. However, the market is open for a pneumatic trip actuator that is cleaner, smaller, cheaper, and easily implemented with shop air. This actuator must be online testable so that you can test the health of the safety system without actually causing a full shutdown to the turbine, which would take up a lot of time and a lot of money. So the goal of our project was to design and prototype a pneumatic trip actuator starting from ground zero that is online testable and can be added to Woodward's product line. At the beginning, we started with very little. We started with a short list of rough guidelines for customer requirements and one identifiable direct competitor.
Speaking of competitors, this is the competitor we were given for inspiration in our design process. They feature more of an external voting system and a couple different voting options. We wanted 2 out of 3 voting logic, and we tried to focus our designs more on internal plumbing for robustness of the system.
Starting with our competitor, Drake, we went into looking at all of how their system worked and how we could improve upon that. Our first semester was focused on gathering info, concept generation, and modeling. Moving into second semester, we had our second iteration of CAD modeling and a period dedicated to high-quality GD&T and engineering drawings. We faced serious time constraints and schedule changes due to manufacturing delays, yet we still managed to pull together both subassembly and full assembly testing, concluding in our project working with a full-scale functioning prototype.
The budget for this project contains CSU funds along with Woodward funding. We had $4,500 to spend through CSU. Our ceiling price for the prototyping at Woodward was $45,000. This covers rapid prototyping costs and everything that we acquire from Woodward.
From the list of customer requirements we started off with at the beginning of our project, we determined there are 9 customer requirements for our device. Building off of our customer requirements and the specification research that we did at the beginning of our project, we determined 11 specifications for our device, most notably fail safely, actuator closing time, and force output. Actuator closing time is our most critical specification as we must shut off steam supply to the turbine within a fraction of a second.
Alright, so moving from our specifications and requirements, we need to actually get concepts and models put down so that we can kind of move into the actual production phase. So we went through various different models and concepts. You can see all sorts of different flow paths and geometries. We had some of the same ideas fundamental in all of them, but lots of different ways of accomplishing that. Now we have a functional diagram of the solution we actually went with.
Alright, so the top set of symbols there are our pilot valves, and as you can see, they run the valve pairs set below. So the first set and the second set, if those are both tripped, you can see that middle path then opens and drains the atmosphere. So the piston on the left is then drained.
So as far as actually achieving that functional diagram, we have kind of an exploded view here. You can see there's a lot of parts, like all hand machined or custom machined. So we have piston rod, piston cap, the piston body itself was machined. The top manifold, the bottom manifold are those 2 kind of rectangular blocks. Those have a whole bunch of different flow paths drilled in them and tapped holes and helicoil.
Next, we have some assembly and testing photos. The first iteration of the manifold required remachining to mitigate the slicing of valve O-rings during assembly. In the bottom left, you can see our first subassembly test, including the top half manifold subassembly with the solenoids, wiring, and pressure transducers needed for testing. Once all the parts had been accumulated, we completed our full assembly of the prototype with the final step of compressing our 1,700-pound spring into our piston cylinder.
While the team was diligently working on drawings to get to manufacturing, I started working on LabVIEW code so that we would be able to test the full system. On the screen here we have the position and pressure code for the LabVIEW. Here is the relay code for LabVIEW, so essentially we wanted to be able to automatically run our relay system in order to test how fast the system ran. So these buttons will output a voltage to run each of the relays together in pairs and all three at once.
This is our wiring setup. We've got a power supply here to run all of our systems, but first off we've got our relay system here. So all three of these are energized, and then when we want to trip a valve or solenoid set, then we de-energize one. Also here we have a pressure transducer set up on the manifold, and there will be 4 pressure transducers at the end to measure the input pressure and pressures within the flow paths. And then lastly we have our position sensor here, which will be connected to the piston head to measure the distance.
Recording data set. Done recording data.
So for our analytical model, we have our test set up here. We used a Python script that was an iterative numerical solution based on a tank blowdown model, and the assumptions that it's quasi-equilibrium and adiabatic. The entire system moves pretty quickly, so there's not a lot of time for heat transfer. Some of the equations we used is the mass flow rate and the temperature of the tank and the pressure inside the tank. Using those 3 equations, we can figure out how long it'll take to drain. So some of our test results from our numerical model, we did some CFD to find a discharge coefficient through our flow paths, and then we used that along with several other test conditions, including the temperature and then an 80 and 120 psi pressure condition to plot out the pressure in the piston versus time, and then use that data to find the piston height versus time. From these results, our trip time should be just within our threshold for both conditions.
Outcomes for our project so far include custom parts that have been toleranced and machined properly, such that we have functioning sub-assemblies as well as a fully functioning complete assembly that replicates our predicted performance based on our analytical model. Some strengths that we have encountered throughout the course of our project include the flexible budget we were given by Woodward, such that we were able to use the rapid prototyping network to get our complex designs machined in time for E-Days. Additionally, all the resources we've had at Woodward have been a huge strength to our project, all the engineers that have provided a lot of support throughout the process. Some limitations we've had include in our schedule. Part delays put us behind in our testing and assembly schedule, but we were able to follow our risk mitigation plan to use our time effectively and still meet our goal to assemble and test our full prototype. Overall, our project has great significance in the steam turbine industry. Our pneumatic trip actuator has the potential to save money and, more importantly, save lives. Suggestions for future work include improving the design to the custom valves, in addition to exploring more novel manifold solutions. Thank you so much to everyone who has helped us throughout the course of our project, in particular our sponsors from Woodward, Jason Brock and Josh Bean, as well as our faculty advisor, Dr. Wise.
Thank you!